All right, so we've all gotten used to the idea of AI writing code for us. But what if the AI could then take that code and make it better, all on its own? That's what we're diving into today. How these evolutionary AIs are learning to optimize software, and trust me, they're coming up with stuff we never would have expected. So I want you to just think about this for a second. What if code wasn't this static thing that a programmer writes and then it's done? What if it was alive in a way, able to learn, to adapt, and to actually optimize itself? Finding solutions that even the smartest human programmers might just miss. Well, that's exactly what's starting to happen. And it all comes down to this idea of an AI that can program itself. The key here, something called an evolutionary agent. So what is an evolutionary agent? Think of it like Darwin's survival of the fittest, but for computer code. It's pretty wild. The AI starts by generating a whole bunch of different code solutions for a problem, a whole population. Then it's brutal. It tests every single one, throws out the ones that don't work well, and keeps the fittest ones. Then it takes the best traits from those winners, mashes them together, and creates a whole new generation of code. It just keeps doing this over and over and over, and with each cycle, the code gets smarter and faster. Okay, so to really see what this could do, some researchers from Hugging Face and Drea for All decided to set up, well, basically a digital Thunderdome for AIs. They took some of the most advanced models out there and threw them into this competition with a simple goal: who can evolve the fastest, most efficient code? So how exactly does a survival of the fittest for code actually play out? Let's get into the setup of this whole experiment. The battleground for this was a benchmark called AlgoTune, and you can just picture it as this brutal obstacle course. We're talking 30 completely different programming challenges, everything from graph theory to linear algebra. So to win here, an AI couldn't just be a one-trick pony. Nope. It had to prove it could improve code across a whole range of problems. Now, the researchers had a really critical decision to make. How should the AIs tackle these problems? They tried two ways. The first was parallel evaluation, basically letting the AI work on all 30 problems at the same time, learning from all of them at once. The second was serial evaluation, where the AI had to solve one problem completely before it could even look at the next one. And as you're about to see, this one little choice, it changed everything. And I'm not kidding. The difference was staggering. Making the AI solve problems one by one, it didn't just slow things down a little. It took 14 times longer. And on top of that, the final code was only half as good. I mean, that tells you something massive right there. Letting the AI learn from a whole bunch of different problems all at once isn't just a nice to have. It's absolutely critical to making this whole thing work. Okay, so now they had the right setup. The AIs were learning in parallel, and they started to evolve. And this is where it gets really interesting. The code they produced wasn't just faster, it was surprising. We started to see a kind of creativity we hadn't seen before. So let's get to the headline number. The champion of this competition, it was Google's Gemini Flash 2.5. After 200 generations of evolving, it managed to make the code run, on average, more than 2 times faster. And just to show you how much it was learning, that was a 24% jump from what it was doing at only 100 generations. And this wasn't just a fluke with one model. Not at all. We saw huge speedups across the board. Proprietary models like Gemini did great, but so did powerful open source models like Google's Gemma and Alibaba's QEncoder. So this isn't some secret sauce from one company. It's a capability that's showing up in all kinds of different AIs. But look, making the code twice as fast is only half the story. The really mind-blowing part is how the AIs got there. They weren't just making little, tiny optimizations. No, they were fundamentally reinventing the solutions from scratch. Let's look at a perfect example. One task was to count connected groups in a network. The original code used a classic method called depth-first search. You can think of that like trying to solve a maze by picking one path and just going all the way to the end before you ever backtrack. Well, Gemini took one look at that and came up with a totally different solution: breadth-first search. That's more like exploring the maze by checking every possible path one step at a time. The result? 95 times faster. But then, get this, Quen came along, looked at the same problem, and ignored both of those methods, it discovered a completely different and way more sophisticated algorithm called union find. I mean, this is pure algorithmic creativity. And that right there is the key insight. This is what's so wild. You've got two different AIs, they start with the exact same piece of code, and they independently discover two completely different, totally valid, and much better solutions. We're talking about more than just tweaking things. This is honest-to-goodness algorithmic discovery happening right in front of us. But the experiment also taught us some things that were, well, really counterintuitive. It completely flipped some of our biggest assumptions about how to get the most out of these AI models. First up, let's tackle the myth that bigger is always better. The researchers tested two models from the QN family. One was a huge general-purpose model. The other was much smaller, but it was specifically trained on code. And what happened? The little specialist model absolutely destroyed its giant generalist sibling. The takeaway is crystal clear. For a task like this, being specialized is way more important than just being big. Okay, so the next thought is pretty logical, right? If you have two champions, why not put them on the same team? So that's what they did. They took their two best performers, Gemini and Quen, and made an AI super team. They expected their combined brain power would smash all the previous records, but it didn't work. In fact, it was a total disaster. The combined super team performed way worse than either AI did on its own. Instead of a super optimizer, they just got a confused mess. It turns out putting your two best players together actually made the team lose the game. So what on earth happened? Why did the dream team fail so badly? Well, it was a classic case of too many cooks in the kitchen. Remember that graph problem? Gemini was screaming, "Let's use breadth-first search," while Quen was insisting, no, union find is the way. They couldn't agree on a fundamental strategy. They just ended up fighting with each other, creating these weird, terrible hybrid solutions that didn't work. It's a great reminder that AI collaboration can be just as messy and complicated as human collaboration. All right, so let's pull back and look at the big picture here. What do all these fascinating results tell us about the future of programming and really our future partnership with AI? For me, there are four huge lessons here. First, the how is more important than the what. That parallel learning environment, it's everything. Second, specialization beats size. A focused expert model is better than a giant generalist. Third, and this is the big one for me, AIs can be genuinely creative, discovering solutions humans might not even think of. And finally, a dose of reality. More AI isn't always the answer. Just like with people, collaboration is complex, and you can't just throw more resources at a problem and expect a better result. When you step back, you realize this isn't really a story about making code run faster. It's about something way more profound. We're witnessing the beginning of a totally new kind of partnership with AI, one where it isn't just a tool that follows our orders, but a creative partner that can actually surprise us with its own original ideas. And that leaves us with one final, pretty massive question. If AI can achieve true creativity in the logical world of code, what happens when we unleash this evolutionary approach on other fields? Think about scientific discovery, drug design, engineering, maybe even art. Where could it go? We're just scratching the surface of what's possible. Thanks for joining me on The Explainer.